Hello everyone, my name is Mahyar Shirvanimoghaddam and I am a lecturer at the School of Electrical and Information Engineering at the University of Sydney. I will go through some of our recent work on channel code design for ultra-reliable and low latency communications. Here is the outline of my talk. I first provide a very brief definition of reliability and flexibility and explain the performance benchmark for code design for URLLC. Then I review some of the candidate channel codes for URLLC, a very brief comparison if then provided. I will then talk about our recent works on short analog fountain codes and reduced complexity order statistics decoder. Reliability in the context of channel coding for URLLC is defined as the success probability of transmitting K information bits with the desired user plane latency. Here we are only concerned about decoding failure, and we do not take into account failure from the perspective of higher layer. That includes, for example, loss of packets due to the violation of the latency requirements. Therefore, every packet must be delivered with a very high reliability to minimize the number of retransmission. And for this, we usually use channel codes with relatively low code rates to guarantee the desired level of reliability. Another important metric to consider when designing channel codes for URLLC is flexibility. That is, the code rate and code word size could not be restricted. Ideally, we like to have bit-level granularity of the code word size and code rate. This is mainly required for enabling hybrid automatic repeat requests to guarantee the desired level of reliability for URLLC applications. There are two main limiting factors in channel code design in the finite block length regime. The first one is not the problem of the code, but is the fundamental gap to the channel limit due to the reduction in channel observation in the finite block length regime, which means that we always have a gap to the channel limit when the code length, block length is finite. To characterize this gap, we use normal approximation as shown in this formula, which basically introduces the channel distortion, denoted by V, to measure the gap to the channel capacity at the given error probability. Here, C is the channel capacity as a function of SNR, V is the channel distortion as a function of SNR as well, N is the block length, and PE is the error probability. To be more specific, we use this formulation to derive the normal approximation benchmark for the binary input AWGN channel because we compare channel codes for URLLC over this channel. So the capacity can be found using this formula. V, the channel distortion, can be found using these two functions, and HS is defined by this integration. The second effect is due to the channel code or the suboptimal decoder, which lead to a gap to the finite block length bound. This figure shows these two effects very clearly. The dashed green curve is the normal approximation at a given code rate and block length and has a gap to the channel limit. The second effect can be clearly seen for LTE turbo code that perform close to the finite block length bound only when the block length is sufficiently large. This is mainly due to the suboptimal decoding algorithm. For example, if the information block length is around 40, we have a huge gap. Here we have a huge gap to the channel limit, and we have a huge gap to the finite block length bound. We now briefly introduce some of the candidate channel codes for URLLC. BCH codes are a class of powerful cyclic codes that are designed for a target error correction capability. That is, the minimum Hamming distance of the code is at least 2t plus 1, where t is the desired number of correctable errors. BCH code has very large minimum Hamming distance and performs very close to the normal approximation bound using the maximum likelihood decoding. In practice, though, we use Breckler-Messi algorithm for decoding BCH codes in binary channels, and over the noisy channels, we usually use soft input decoders like order statistic algorithm. Both algorithms, however, are very complex, which prevents the adoption of BCH codes in URLLC applications. Another powerful class of codes is convolutional codes, which were proposed by Elias in 1955. The code has a simple structure and can be implemented using shift registers and binary operations. The code is fully characterized by the memory order and input and output lengths. We usually use Viterbi decoder or BCJR to decode convolutional codes. For convolutional codes to perform close to the normal approximation bound, the memory order must be set to a very high value, which significantly increases the decoding complexity. In fact, the decoding complexity increases exponentially with the memory order. Turbo codes were proposed in 1993 as a parallel concatenation of two convolutional encoders which use MAP decoding. The code performs very close to the finite length bound when the block length is sufficiently large and has been widely used in 4G system because of their very efficient encoder and decoder. However, in moderate and short block length turbo codes with iterative decoding show more than 1 dB gap to the finite length bound. And the code, one other advantage of the code is that it is flexible and support both chase combining and incremental redundancy HARQ. Another very important class of linear block codes is low density parity check codes, which were originally proposed by Gallagher in 60s and rediscovered in 90s. The parity check matrix of the code is sparse, which enables efficient and low complexity message passing decoding algorithm. The codes perform very close to the channel limit in large block lengths using iterative message passing decoder. And they have been recently standardized for the 5G enhanced mobile broadband data channel. They, however, suffer from gap to the finite block length bound and error flow in short to moderate block lengths, especially when the code rate is low. The most recent channel code originally proposed by Aricon is Polar code. The code can achieve the capacity of the binary memoryless channel using low complexity encoding and decoding in asymptotically large block lengths. The main concept behind the code is channel polarization, that the code polarizes the channel into n synthesized channels with capacities either 0 or 1. The code performs very close to the finite block length bound using maximum likelihood decoder, but loses performance when using practical successive interference cancellation. The code also suffers from latency due to the successive decoding. Now let's compare these candidate channel codes for URLLC. Here we consider the maximum likelihood decoder to compare the code performance only and eliminates any loss due to the suboptimal decoder. For tail-biting convolutional code, we used Viterbi decoder. The channel code rate is 1/2 and the block length is 128. As can be seen, extended BCH code, so this one, perform very close to the normal approximation bound. The other two good codes are tail-biting convolutional code with a very large memory order. Here the memory order is 14, and non-binary LDPC code designed over a very large Galois field performs well too, but the gap to the finite block length bound increases when the error rate is very low. The other codes are polar codes and binary LDPC codes, and they performs poorly in comparison to the other codes and have a huge gap to the finite block length bound. We now compare polar codes, LTE tail biting convolutional codes, LTE turbo codes, and LDPC codes at different code rates and information block lengths. As can be seen, by using practical decoders, CRC-aided polar code performs very close to the finite block length bound. For example, here at rate 1/6, it performed very close to this bound. Here as rate 1/3, it performs very close to this bound. And then the next one, which is the tail biting convolutional codes that performs also good. The other two codes, like the LDPC and turbo codes, they have a large gap to the finite block length bound, and LDPC codes shows some error flow in low code rates and for moderate and short block lengths. To summarize, under maximum likelihood decoding, BCH codes outperform all other codes thanks to their very high minimum Hamming distance. Other codes are mainly designed to provide good performance while maintaining the decoding complexity at a reasonable order. And using practical decoders, polar codes shows very good performance with no sign of error flow. LDPC codes, however, suffer from error flow at short block lengths, and turbo codes performs well only at large block lengths. So this figure compares different codes using practical decoders at different SNRs and rates for a given target error probability. As can be seen, BCH code with OSD decoder performs very close to the finite block length bound, while other codes like LDPC and polar codes show a relatively large gap to the finite block length bound. This shows a potential advantages of BCH codes and calls for fundamental breakthrough in designing low complexity decoders for BCH codes. We now briefly explain the order statistic decoder and our recent work on reducing the complexity of the algorithm. The order statistic decoder is a maximum likelihood like decoder which is designed for binary linear codes that runs in two main stages. First, the received signals is ordered according to the bit level reliabilities, and the generator matrix is accordingly reordered, and the generator matrix is then converted to the systematic form by using Gaussian elimination. In the next stage, the first k-bit position, referred to as most reliable basis or MRB, is modified by bit flipping to generate test error patterns. Each test error pattern will be re-encoded and the distance to the received signal will be calculated. After generating all possible test error patterns, the one with the lowest distance to the received signal will be output. The maximum number of bits flipped is called the order of the OSD algorithm, and it has been shown that for a code with the minimum Hamming distance D, the order of OSD decoder should be at least D/4 to achieve near maximum likelihood performance. In the original OSD algorithm, the number of test error patterns is very large, which makes the algorithm very complex, especially when the order is high. In fact, for an ordered DOSD algorithm, one need to generate a large number of test error patterns, usually in the order of K to D. However, one can discard some of the test error patterns to significantly reduce the complexity. For this purpose, we propose a novel approach called segmentation discarding algorithm to effectively discard some of the non-promising test error patterns. For this, the most reliable bit positions will be divided into several segments, and then some of the segments that are less likely to generate promising test error patterns will be discarded. This figure shows an example of the proposed algorithm that first divides the most reliable bit position into several segments, and then those segments that are less likely to generate good test error patterns will be discarded. Here, these segments will be discarded and these segments will be retained. So here we compare the performance of the proposed segmentation discarding algorithm in terms of block error rate and the average number of test error patterns with the original OSD algorithm. As can be seen, the proposed approach performs very close to the original OSD in terms of bit error, block error rate. But with much lower number of test error patterns. In fact, with this very basic idea, we can reduce the number of test error patterns by an order of magnitude. The improvement is consistent across different code rates and order of OSD algorithm, and the number of test error patterns is significantly reduced by using the segmentation discarding algorithm without any significant loss in terms of the block error rate. We can further reduce the complexity of OSD algorithm by using some necessary and sufficient conditions to discard test error patterns. In our latest work, recently submitted to the IEEE Transactional Information Theory, we analyzed the performance of the OSD algorithm and characterized the Hamming distance and weighted Hamming distance in each reprocessing stage of the algorithm. We then devised sufficient and necessary conditions and accordingly designed several low complexity algorithms, which perform very close to the original OSD in terms of the block error rate, but with a significant lower complexity. Here we have a very basic comparison between different codes in terms of complexity of the decoder and the gap to the normal approximation. As can be seen, OSD can be designed in such a way to offer different levels of reliability and complexity by using segmentation discarding algorithm. Polar codes with successive cancellation list decoder also offer competitive performance while they suffer from latency issue because of the successive nature of the decoder. As the last section of this part, we will briefly introduce our recent improvements to analog fountain codes for ultra-reliable and low-latency communications. Wireless communication systems usually use adaptive modulation and coding that is based on the feedback from the transmitter about the channel state. The best channel code rate and modulation order are selected by the transmitter. However, this feedback process incurs 5 to 8 millisecond latency, which indeed violates the latency requirements of many URLLC applications. And this signaling overhead to obtain channel state information will be relatively high for short packets. An alternative approach to adaptive modulation and coding is to use self-adaptive codes. These codes adapt to the channel condition automatically without any channel knowledge. Some examples include Luby transform codes, Raptor codes, and some other codes which have been mainly designed for binary channels and have been optimized for erasure channels in the asymptotically long block length regime. In 2013, we proposed analog fountain codes for wireless channels and showed that they perform very close to the channel limit in the AWGN channel at asymptotically large block lengths. For AFC, the information block is first encoded using a high rate LDPC code or precoder. This could be also a BCH code, which is more appropriate for short block lengths, and then modulated using BPSK. And then we use the AFC code or the modified version for short block lengths code to generate a potentially limitless number of coded symbols to be transmitted over the channel. To perform the decoding, we use message passing decoder for AFC and then use a binary decoder for the outer code. For example, we use again message passing decoder if we use LDPC code as a precoder. The AFC encoding is very simple. First, a degree D is drawn from a degree distribution function, and then the distinct information symbols are selected at random and linearly combined using real weight coefficient, also selected from a weight set to generate each coded symbols. Here in this figure, we show the code performance over the AWGN channel in the asymptotically large block lengths. We can see that the code performs very close to the channel limit. However, in the short block lengths, for short block lengths, we need to do some modification, for example, in the way that we select information symbol to generate each coded symbols. Otherwise, we lose the performance at short block lengths. Here is an example of the code performance in the short block lengths regime. As can be seen, there is a huge gap to the normal approximation bound, especially at low SNRs. To overcome this problem, we propose a modification to the information symbol selection and weight set design for AFC encoding. Here we try to maximize the minimum Euclidean distance between the AFC coded symbols. This will lead to a significant improvement in the error performance in short block length region. For example, here we compare the minimum Euclidean distance between AFC symbols in the original AFC code, and here we showed that using the new design and the new weight set design, we can significantly increase this minimum Euclidean distance, which translates to a better error rate performance. Using this approach, we can significantly reduce the gap to the normal approximation bound. Here we can see that we get very close performance in terms of the average block length to achieve the error probability of 10 to the minus 4 for this information block length. As the code is generated randomly, the number of symbols required for successful decoding is random. Here we show the CDF of the block length to achieve packet error rate of 10 to minus 4. As can be seen, when the SNR increases, the CDF becomes narrower, which shows the potentials of the codes to be used for guaranteed reliabilities and latency. However, in lower SNRs, we still need some further improvements. Another advantage of the code is that even though we are using message passing algorithm, there is no sign of error floor. And this is mainly because of the use of powerful precoder. For example, here we use LDPC code, and the result improves if you use BCH codes. With this very simple design, we can significantly improve the error rate performance of AFC code. For example, the original AFC was designed and optimized for asymptotically large block lengths, but with this modification, we can improve it significantly. Analog fountain codes can be carefully designed for URLLC, which offer a low complexity encoder and decoder, 1-bit granularity for code rate and block lengths, and near optimal performance at different SNRs. Another advantage of the code is that the code does not need channel state information at the transmitter side, which significantly reduces latency due to the feedback. There are some challenges too. For example, the precoder should be carefully designed. If we are using, for example, BCH code, what is the channel code rate for this code, and whether it's better to use low rate code or high rate code. Another problem is about the CDF of the number of symbols required at the receiver side, and the CDF should be very narrowed to guarantee reliability and latency requirements of URLLC applications. As final notes for this part of the talk, it's important to note that the channel code for URLLC has not been standardized yet. There are some solutions like polar codes and LDPC codes which have been widely studied. While LDPC codes offer very low complexity iterative decoders, they suffer from error floors at low rates in the short block length regime. Polar codes, on the other hand, show excellent performance at low rates in the short block length regime, but suffer from latency because of the successive nature of the decoder. There are some other good codes like BCH codes that achieve the best result under the maximum likelihood decoding, but current OSD decoders are very complex. Moving forward, I believe further research is needed to reduce the complexity of OSD decoders to enable fast and reliable and efficient BCH decoding to gain the advantages of very large minimum Hamming distance of these BCH codes. Moreover, novel codes like analog fountain codes provide some advantages due to their self-adaptive nature, which make them suitable for very low latency applications. Thank you for listening.